this lecture, we're going to discuss control volume energy analysis. So this is conservation of energy for a control volume or an open system. So what we've looked at so far is closed systems. Closed systems are also known as a control mass. So remember, a closed system boundary has no mass flow across it. What we're going to turn our attention to now, though, are open systems, also known as control volumes. So the big difference here, of course, is that we're now going to allow mass flow to cross the boundary. So we're setting a region of space aside for study rather than a portion of mass. So key thing, mass may cross our boundary. So what we need to do is go back and take a look at our conservation of energy equation and make some adjustments to it so that it's valid for this new situation. So to do that, we're actually going to start with the equation we already have. So we're going to start in a few moments here with our energy conservation equation for a control mass or a closed system and work with it to develop a conservation of energy equation for a control volume. So we're going to use this situation here to illustrate how this works. So let's say that we have a system of some kind, and it really doesn't matter what's inside of here. There could be multiple components in here, there could be just one component. We're going to identify, first of all, a control volume. So we have a control volume boundary here, and the big difference between this and our system boundary for a closed system is there is now mass flow at that location and at that location across our system boundary. So we need to take that into account. Well, like I say, our starting point for this is going to be the equation we already have for conservation of energy for a closed system. So we're going to develop an equation for conservation of energy for a control volume, that's our new situation, by applying the first law for a control mass. So conservation of energy for a control mass. So here's our system again, just shown at two different times. At time t, and then some small time later, t plus delta t. And remember, we have a control volume boundary around this thing. And for clarity, I just haven't drawn that control volume. Now at time t, we're going to identify a control mass boundary that looks like this. So take a look at the left one here, which is at time t. So notice that this control mass boundary includes all of the material inside of this system, but it also protrudes into this inlet pipe a certain amount. Now realize this solid red line is a control mass boundary or a closed system boundary, so no fluid is allowed to cross that boundary. So as we progress from time t to time t plus delta t, that solid red line has to move with the fluid because nothing can cross that boundary. So after time delta t is passed, we see that our control mass boundary still includes all of the material inside of the control volume, but it now protrudes into the exit pipe and it no longer protrudes into the inlet pipe. So we can take our existing equation for conservation of energy for a control mass and apply it to this control mass that we've shown here. And from that, we'll get a conservation of energy equation for the control volume. So let's see how that's going to work as we go forward here. So start off with conservation of energy for a control mass. Q minus W equals delta E. And that's the equation we've been working with up to this point in the course. Now what we want to do is take a look at our system here at these two times. So starting off at time t, remember that that's when our control mass protrudes into the inlet pipe. So what we say is that the amount of energy in the control mass, remember that's the solid red line, at time t is going to be equal to the amount of energy in the control volume. So notice that would be the energy contained inside of this system, plus the amount of energy in this inlet section, and that is this portion. So the total energy in the control mass will be the sum of those two, what's in the control volume and what's protruding into the inlet pipe here. Now we do exactly the same thing at time t plus delta t. So again, the amount of energy in the control mass at time t plus delta t is the energy in the control volume at that same time. So notice that's the energy contained in this fluid, plus the energy in this portion of the exit pipe where material has been pushed out during this time delta t. So both of these statements are just adding up all of the energy in our control mass by the energy in the control volume and this extra bit to account for the inlet pipe and the exit pipe. So this is the first step in developing a conservation of energy equation for a control volume. So the delta E in this equation is the change in energy of our control mass during this time delta t. So it's just the difference between these two things. So this minus this is delta E. So we can proceed and write that down. So delta E, and that's this, so these are the same thing, we're just expanding this, is the energy in the control mass at time t plus delta t minus the energy in the control mass at time t. So that's what we mean by delta E in this equation. Well, we just replace both of these with the corresponding expression taken from these two lines. And when we do that, we get that the change in energy for our control mass is equal to the change in energy of the control volume, that's that portion, plus the energy in the exit pipe minus the energy in the inlet pipe. So notice here we're getting a connection between the change in energy of the control mass, so that's what this side is, and the change in energy of the control volume. That's what this side is. The difference between the two is what's happening at the inlets and the exits. So now we want to keep working with this, and we want to remind ourselves that each of these energies that we're talking about here, all of these capital E's, are total energy. And total energy is the sum of three contributions: internal energy, kinetic energy, and potential energy. The other thing that's happening in this line is that the total amount is being written as a product of the specific energy, so each of these is energy per unit mass multiplied by the mass. So capital E is mass times the specific internal energy and the kinetic energy per unit mass and the potential energy per unit mass. Now this particular line right here is written for the energy in the exit, so that's why it has this subscript E on each one of these terms. I'm just using the energy in that exit pipe as an example of how we can expand this total energy into its three contributions. Now up to this point in the course, when we've talked about this kinetic and potential energy, we've just represented them by the initials Ke and Pe like this. But at this stage, we want to write these two energies in terms of other more useful variables. So remember, this is the kinetic energy per unit mass, because that's the internal energy per unit mass. So each of these is an energy per unit mass. Well, the kinetic energy per unit mass is equal to the velocity of the fluid squared divided by 2. So v squared over 2 is the kinetic energy per unit mass. Notice it still has this subscript on it, E, to remind ourselves that here we're talking about the energy at the exit. So the kinetic energy of the fluid leaving our control volume per unit mass is v squared over 2. Remember that the kinetic energy of an object, if you pick something up and chuck it across the room, its kinetic energy is 1/2 mv squared. Well, its kinetic energy per unit mass would be that divided by its mass, so that's just v squared over 2. Likewise, we want to do a similar thing with the potential energy. Well, the potential energy per unit mass is g, the acceleration due to gravity, times z, where z is the elevation or the height of that particular exit. So here we're assuming that we're using Z to measure the distance up from some datum. So what we want to do, now that we've written our total energy as a sum of these three contributions, is bring this back into our first law. So here we have our change in energy of the control volume being equal to Q minus W. So this is the heat transfer that occurs in this time delta T, and the W is the work transfer with the surroundings that occurs in this time delta T. And if we were to just stop there, if we were to just look at this portion of this equation, that's essentially first law for a closed system. Q minus W is the change in total energy. But now that we have an open system and we have material entering and leaving, we need these two extra terms that have come in here. This one to account for the energy transported in during that time delta T at the inlet, and this one to account for the energy transported out of our control volume during that time delta T at the exit. So this is a conservation of energy equation modified for an open system because it accounts for what's happening at the inlets and at the exits. Now there's a few things we still need to do to this equation to get it in a more useful form for applying to different problems. So we're not to the end of our development yet, but the essential features are starting to become clear here. The fact that we need to account for what's happening at the inlet and the exit. So a few things left to do. The first thing we want to do is that it is typical, or it is more useful, to have this equation on a rate basis. Now if we just go back and think of units here, Q is a total amount of heat transfer that happens during time delta T. Likewise, W, total work transfer that happens during that time delta T. So if we were talking in SI units here, the units of those would be kilojoules or perhaps joules. So an amount of heat transfer, an amount of work transfer, and an amount of energy change. All the terms, of course, would have the same dimensions. It is more useful if we have this equation on a rate basis, so that each of these is the rate at which heat is being transferred, the rate at which work is being transferred, the rate at which energy is being transported in and out of our control volume. So to convert this equation to a rate equation, we divide it by delta T and take the limit as delta T goes to 0. So let's see what that does to the equation. Well, first of all, we look at the left-hand side and we see we now have the rate of change of the energy in the control volume with respect to time. So I'm just going to go back and show how that works. So remember what we've done. We've divided this by delta T and taken the limit of this as delta T goes to 0. Well, that's the definition of a derivative. The change in the quantity divided by delta T, and the limit of that as delta T goes to 0 is the definition of a derivative. So that's why here we write that as dE dt, and it's the energy in the control volume. We'll be talking lots about that term as we go forward, but it's called the unsteady term. Moving over to the right-hand side of the equation, we first see the Q. The only thing that's happened here is that Q has been replaced by Q dot. Q dot is just a shorthand notation to indicate the rate of heat transfer. So this is similar to dQ dt, but it's just a shorthand notation indicating the rate of heat transfer. Likewise, W dot is now a rate of work transfer. So the units of all of these terms now, instead of being kilojoules, will be kilowatts, or instead of joules, they will be watts, a rate of energy transfer. If we look at the inlet and the exit term, notice that everything inside of these parentheses is still the same. Nothing has happened there because all of those are on a per unit mass basis. But what has happened is instead of these being masses, they are now a mass flow rate. So again, the dot on top indicates a mass flow rate. So m dot is mass flow rate, and in SI the units would be kilograms per second. So now we're getting closer to the conventional form of this conservation law, but we're still not quite there yet. The thing we need to think about, and that we've glossed over in our shift from a control mass to a control volume, is this work transfer term. Because it turns out that there's actually two distinct ways that there can be work transfer between this system and the surroundings. And we need to separate those out because they're two quite different effects and we need to distinguish between them. So for the next little while, we're going to be discussing this work term. So that brings us to the topic of flow work. So we want to go back to the inlet of this control volume. So that's what we're showing here. The rest of the control volume is here as well. We're just zoomed in on the inlet. So just a reminder, we have our control volume boundary here. And remember, a control volume boundary can have flow across it. So that boundary's there, and we're at the inlet here, so there's flow across there. Well, the reason that we're revisiting this inlet is that when this material moves into our control volume, we need to recognize that the surroundings, and that's everything out here, are going to be doing work on our system. Remember what work is? Work is a force acting through a displacement. So the surroundings out here are going to do work during this time delta t to push fluid into our control volume. Now, to try and illustrate that, what I've done is I've gone into this inlet pipe and I've shown a little piston in there. Now, in reality, what is over here could be anything. It could be an elevated reservoir that is causing this flow. There could be a pump out here that is causing this flow. We're just replacing whatever that is with this little piston that is going to push this material into the control volume. So during time delta t, all of this fluid is going to be pushed into our control volume. Well, that represents work being done on our control volume because it's a force acting through a displacement. So that type of work is called flow work. So that's what's going to happen here. As time goes on, that material is going to get pushed into the control volume. So the surroundings do work on the system to push fluid into it. That's what flow work is. So the next thing we need to do is quantify that flow work. Figure out how can we put a number to it. How can we determine how big that flow work is. In these open system analysis, we absolutely have to account for the flow work. In many cases, it's the most important energy transfer going on. So we need to figure it out. We can't just neglect it and hope that it's not very important. It certainly is. So to quantify this flow work, we need to think about what properties of the fluid in that inlet pipe are going to contribute to that work calculation. Well, realize that what's happening here is this material is being pushed into our control volume via a constant pressure process. We're looking at a steady situation here, so the properties here are not changing with time. So we have some pressure in here. So this P sub I is the pressure at this inlet pipe. Remember, the subscript I reminds us we're talking about an inlet as opposed to an exit. Small vi, remember what that is? That's the specific volume, so the volume per unit mass. And we're saying that during this time, delta t, that we're considering, the amount of mass that gets pushed into our control volume is dmi. Again, the subscript I with the usual meaning there. These are the variables we need to figure out how big this work is. So the amount of work that is going to be done, and we call that delta W because it's the small amount of work done during time delta t. We remind ourselves we're talking about flow work here in our notation, and we remind ourselves that we're talking about the inlet. So that's what the left-hand side means here, the amount of flow work done at the inlet during time delta t. Well, that's going to be equal to the pressure there times the change in volume. So for a constant pressure process, P times the change in V gives us that work. So we're just changing this dV here to the specific volume times dm. Remember, this volume, if we just talk SI units, would be cubic meters. This is cubic meters per kilogram multiplied by the mass in kilograms. So capital V here is just replaced by small v, small m. So the flow work at the inlet that happens during time delta t is that. So if we change this to a rate, so just going back here, we're going to take this and divide it by delta t and take the limit as delta t goes to 0. Then this becomes W dot over here. We're still talking about flow work and we're still at the inlet. And that's going to be the pressure at the inlet times the specific volume at the inlet multiplied by the mass flow rate. Notice this is now m dot, the mass flow rate. The other thing that I've done in this line is I've put a negative sign in front of here. Now remember our sign convention for work, which we need to get right even for this flow work. When work is done on the system by the surroundings, that is negative work. And that's exactly what's happening at the inlet. The surroundings are pushing fluid into the system, so the flow work at the inlet is negative. So that's why I've added this negative sign here. So at the inlet, the flow work, or the rate at which flow work is being done on our system, is minus P V m dot. Now we've been focusing on the inlet, but we could have had this entire discussion at the exit if we wished. And everything that we've talked about would be the same. There's only two differences. One, first of all, these properties, the pressure and specific volume, would have to be evaluated at the exit, so they have a different subscript. And the second difference, at the exit, the system is pushing material out into the surroundings. So the system is doing work on the surroundings, and that, according to our sign convention, is considered positive work. So therefore, this is positive instead of negative. Other than that, everything we said at the inlet applies at the exit. So the total flow work is the sum of these, or the total rate at which flow work is being done. So notice now here we just have W dot flow, no additional subscript on it because it includes what's happening at the exit and what's happening at the inlet. Now notice these two things in general are very, very different from each other. So there certainly is net flow work in many, many situations. So this is a very important term to account for. Now what we do is bring this back into our current form of conservation of energy. So first of all, I want to just indicate what has not changed here. The left-hand side has not changed, and the heat transfer rate on the right-hand side has not changed. I've just added this CV designation here to explicitly say we're talking about heat transfer with the surroundings, between the control volume and the surroundings, but this has not changed. Another thing that has not changed as a result of what we're doing here are these two terms that account for the energy transport at the inlet and at the exit. However, what has changed is this term that used to be just W dot has been split into two parts. One part is the flow work that we've been talking about, and the other part is now written as W dot CV. This is called the shaft work. And this will play a very, very important role in this equation for many types of systems that we're going to be looking at. So the total work that we had earlier, W dot, has been split into these two contributions, flow work and shaft work. And they've now been written explicitly as two separate parts of that total work. Now, what is the shaft work? Well, shaft work is exactly as its name implies. If our control volume is connected to the outside world, in other words, the surroundings, by a shaft of some kind, then there's an opportunity for a work transfer through that shaft. Now, typically that's a rotating shaft, so there's a torque applied through an angular displacement, and so that gives rise to work, the same way as a linear force acting through a displacement gives rise to work. In the rotational sense, a torque acting through an angular displacement is also a mechanical means to have work transfer between the system and the surroundings. So a very typical example of that would be if we were applying this equation to a turbine or a compressor. There would be a shaft sticking out of our control volume and a work transfer in that shaft that we need to account for. So that has nothing to do with the flow work we've been talking about. It is a mechanical work that is happening through a solid connection of some kind of shaft. So that we will be calling the shaft work from now on. And so the total work is the shaft work plus the flow work. Now we would really like to clean this equation up a little bit, and there's a little bit we can do to tidy it up and make it in a little more convenient form. And that involves taking these two flow work terms and combining them with this inlet and exit term. Because if you take a look, you'll notice here we have an m dot I, and here we have an m dot I. Likewise, m dot E there and m dot E here. So we can take these two terms and move them over and combine them with what we have here so far. So that's what we do. So that's what's happened here. Our unsteady term, heat transfer term, shaft work, nothing's happened there, but we've taken our flow work term and it now appears here and here. So that's the flow work at the inlet and the flow work at the exit. And the mass flow rate that goes along with that is out front here and here. Now, this brings us back to a property that we've talked about before very briefly. And when we introduced it earlier, we said that later on there will be a much more physically meaningful way to describe the meaning of this property. And this property is U plus PV. So in thermodynamics, we redefine U plus PV, that particular combination of properties, as the enthalpy, H. So enthalpy is U plus PV. But now that we've arrived at enthalpy by developing a conservation equation for open systems, we see physically exactly what enthalpy is. What is enthalpy? Enthalpy is internal energy plus the flow work. So it's an extremely convenient property, because if we use enthalpy in these terms, we're simultaneously accounting for the internal energy that that material carries with it as it enters and leaves our control volume, but we're also accounting for the flow work done at the inlet and the exit. So the last thing we're going to be doing to this equation is replacing those two U plus PVs with enthalpy. And so that's what we see here. So our final energy balance equation for a control volume is as follows. And this is going to be the starting point for every problem that we do in this section of the course, where we're doing an energy balance or applying conservation of energy to a control volume or to an open system. So notice U plus PV is now enthalpy. So an extremely important property for open system analysis. Now I should point out one other thing that has happened here. You'll notice these summation signs have suddenly popped into the picture. Well, our entire development of this equation was based on us looking at that relatively simple system that we started off with that happened to have one inlet and one exit. Well, there's nothing saying that our open system needs to be restricted to only one inlet and one exit. We're certainly going to see situations later on in the course where we have multiple inlets and multiple exits. So to make this conservation equation more general, we show that we can have any number of inlets and any number of exits. We just need to include one of these terms for each inlet and one of these terms for each exit. Next, I want to take a look at some common simplifications to this equation. So the first one we're looking at here is steady state. So if we're looking at a situation that is operating at steady state, which means none of the properties at any point in the system are changing with time, then we could do a steady state analysis. Now the only impact that that has on our conservation of energy equation is that the left-hand side is now 0. Remember what that left-hand side used to be? The rate of change of energy in the control volume with respect to time. So a steady problem means that quantity and no other quantities are changing with respect to time. So that derivative is equal to 0 for steady state. And that's a fairly common assumption. We are going to do some unsteady problems, but quite a few of the ones that we'll do, especially early on, will be steady problems, and we'll be making that assumption. One further assumption that is quite common is that we're analyzing a component or a system that has just a single inlet and a single exit. Well, if we're analyzing a component that has a single inlet and a single exit, we don't need these summation signs. There is only one of each of these terms. And if it is also steady state, which we are still saying, then the mass flow rate at the inlet has to be the same as the mass flow rate at the exit. So in this version, we've factored that mass flow rate out, and it's right here. Now typically, if that's the case, we don't bother with a subscript on the m dot because it's the same at the inlet and the exit. So we factor the m dot out, and then we can show that this term consists of an enthalpy change, a kinetic energy change, and a potential energy change. The last thing I want to talk about in this lecture is conservation of mass. Now we've looked at conservation of energy, so that's certainly one of the conservation laws that we'll have at our disposal when we start doing problems, but we don't want to overlook conservation of mass because we very often need to use it as well to come up with enough equations to solve our system. So conservation of mass for a control volume is as follows. Again, the left-hand side is the unsteady term, only now the quantity that we're studying is the mass in the control volume, not the energy in the control volume. So the left-hand side is dm dt, where the m is the mass inside of our control volume. On the right-hand side, again, we need to account for what's happening at the inlets, and there can be more than one of those, and what's happening at the exits. So this is just a summation over the inlets of the mass flow rate minus the mass flow rate at the exits. So that's our conservation of mass equation that we can apply to any of the systems that we're going to analyze. Now the last thing I want to talk about here is a connection between mass flow rate, and that could be either one of these things, whether we're looking at an inlet or an exit, doesn't matter for this discussion. So the connection between mass flow rate and three other characteristics of those inlets and exits. So m dot is equal to A times V over the specific volume. So in this expression, this A is the area. So the inlets and exits that we're talking about will be pipes or ducts of some sort, and that A is the cross-sectional area of that duct or pipe. The V in this equation is the velocity, or the speed at which the material is moving. Now if you think about the numerator of this, so the product of velocity and area, that is a volume flow rate. Again, if we just think in SI units here, this area would have units of meters squared. The velocity would have units of meters per second. So the product AV is cubic meters per second. So the product, or the numerator of that expression, is a volume flow rate, either at the inlet or exit, whichever one we happen to be looking at. And the denominator of this is the specific volume. So that's the volume per unit mass. So if you take the volume flow rate, divide by the volume per unit mass, and remember the units of it, if we just use SI as an illustration here, the units of this are meters cubed per kilogram. So we take this, divide it by this, and we get our units for m dot, which is kilograms per second. So this is an important expression to remember and use because it relates the mass flow rate at an inlet or an exit to these other properties. And so we may be given these and need to calculate this, or we may know this and we're looking for one of these. It varies just exactly which one of these we're looking for, but it's an important expression that relates those things together.